Welcome to my DDS. My name is SiQi. I'm a Ph.D. candidate at the Dynamic Systems Lab led by Professor Schoellig. I'm happy to give this talk today and share some of the research results from my Ph.D. The title of my Ph.D. thesis is Neural Networks as Add-on Modules for Improved Performance of Robot Control Systems. Empowered by the advances in both hardware and software, autonomous robots are envisioned to become reliable human companions in various applications. We can visualize different robot applications over this 2D plot. The horizontal axis shows how much we know about the robot system, while the vertical axis shows the level of safety we wish to achieve. In traditional applications, robots are programmed to perform repetitive tasks in well-characterized environments. However, in more recent applications, robots are expected to operate in increasingly versatile environments that require continuous learning and adaptation. We can also visualize different robot decision-making approaches in the literature over this 2D plot. Classical control approaches typically start with a prior model of the robot. By exploiting the system structure, we can provide different levels of safety guarantees. On the other hand, we also have data-driven approaches. In particular, reinforcement learning is the standard machine learning framework to address the problem of sequential decision-making under uncertainties. In contrast to classical control approaches, reinforcement learning can be applied when the model of the system is not known. However, providing safety guarantees can be typically challenging. Recently, we see a trend where control approaches are integrated with data-driven approaches to improve the generalization and performance of robot decision-making algorithms while still preserving desired safety properties. In our survey paper, we summarized the recent literature into 3 categories. The first category is safely learning uncertain dynamics, where machine learning models are safely incorporated to standard control frameworks to improve performance. In these works, probabilistic or hard constraint satisfactions are often guaranteed. We also have safe and robust reinforcement learning algorithms that encourage safe exploration in the learning process and achieve soft constraint satisfactions. Lastly, we have safety filter and certification methods which can be augmented to and thereby provide probabilistic or hard safety guarantees to learning controllers that were not initially designed to be safe. The work in my thesis generally falls under these 2 categories with an emphasis on neural network-based approaches. In particular, the goal of my thesis is to develop data-driven approaches that safely and efficiently exploit the modeling capability of neural networks for robot control applications. My thesis is broken down into the following 3 parts. In the first part, we propose an offline neural network learning approach that allows us to improve the robot control performance when a detailed dynamics model of the robot system is not available. In the second part, we introduce an offline-online learning framework that allows us to leverage the learning experience from a source robot to enhance the control performance of a second robot. In the last part, we consider a scenario where we have minimal offline data for an unknown robot system and develop a safe online neural network learning approach that enables model-based control techniques to be applied in presence of dynamic uncertainties. We will start from the first part. In this part of the work, we consider trajectory tracking problems, which is part of different applications such as UAV-aided inspection, automated manufacturing, and autonomous driving. In these applications, high accuracy tracking is often required for safe operation and optimized performance. However, due to the nonlinearities in the dynamics as well as unknown disturbances, achieving high accuracy tracking can be challenging. In the literature, there are different approaches to achieve basic tracking functionalities. The most common technique is PID control. Despite its simplicity, it can be shown in theory that perfect tracking cannot be achieved for arbitrary trajectories. On the other hand, we also have model-based control techniques such as model predictive control and iterative LQR that allows us to optimize the performance of the robot given a dynamics model. The performance of these model-based techniques, however, are often limited by the accuracy of the model. Lastly, we also have adaptive control and robust control approaches that are targeted to address the issue of model uncertainties. But these approaches are typically restricted to systems with a particular structure or can lead to conservative performance. In our work, we consider the following setup, where we have a black box robot baseline control system that does not necessarily have a good tracking performance. We then augment the system with a neural network inverse dynamics module that adapts the reference sent to the baseline system with the goal to establish an identity map from the desired output to the actual output of the system. In contrast to other learning-based control approaches, in our work, we leverage the existing controller available to the robot and use data to enhance the closed-loop performance. This add-on learning architecture makes the overall approach more data efficient and also less prone to instability issues. Here is an overview of our approach. We assume that the robot baseline system is represented in the following discrete time control file form. From control theory, we can show that if we are at a state xk, the input and output of the system are related as follows. Here, f and g are nonlinear functions of the system state x, and yk plus r is the output of the system r steps ahead. The variable r here is called the relative degree of the system. Intuitively, the relative degree is the inherent delay of the system, or the number of sample delays between applying an input to the system and observing a corresponding change in the output. Based on this input-output relationship, we can then derive an inverse map to achieve exact tracking. Ydk plus r here is the future desired output. When the dynamics of the system is not known, we can train a neural network add-on module to approximate the inverse map based on the system data. We verified our approach in quadrotor impromptu tracking experiments, where the goal is to have a quadrotor track arbitrary hand-drawn trajectories accurately in single attempts. Here we see the performance of the robot baseline control system. By augmenting the neural network inverse module, we can significantly improve the tracking performance, and this performance improvement can generalize to different trajectories. We tested the approach over 30 test trajectories and observed that the add-on module led to an average of 62% tracking error reduction. To summarize, in this work, we proposed a novel neural network inverse dynamics learning approach to enhance the tracking performance of black box robot control systems. In contrast to other learning-based control approaches, the proposed neural network add-on module does not modify the underlying controller of the robot baseline system, and therefore makes the overall approach more data efficient and less prone to instability issues. The proposed approach can improve the tracking performance on arbitrary trajectories. In our paper, we also provide a stability analysis of the proposed approach and additional theoretical insights to further improve data efficiency. In the first work, we showed the efficacy of the neural network inverse dynamics learning approach for enhancing the tracking performance of robot control systems. An implicit assumption in the first work and neural network-based approaches in general is that the neural networks are trained on datasets that sufficiently cover the operational space. In practice, the neural networks are often trained in a trial and error manner until a satisfactory performance is achieved. This trial and error process can be either inefficient or unsafe for real-world applications. In our follow-up work, we then ask the question, how do we systematically design training trajectories for data collection? To address this question, we propose an episodic training trajectory generation framework that generates smooth, informative training trajectories. In each episode, we first identify the points at which the neural network is the most uncertain. We then optimize a spline training trajectory that passes through these informative points. After training on the trajectory, we see that the neural network module becomes more certain over the region where it initially had higher predictive uncertainties. We repeat this process until the uncertainty over the neural network input space is sufficiently low. In another extension, we investigated how we can adapt the inverse learning approach to systems with unstable inverse dynamics, or non-minimum phase systems. Examples of nonlinear phase systems include inverted pendulum and parallel parking. For these systems, straightforward applications of the proposed inverse learning approach would not work. The inherent instability of the inverse can cause numerical issues and worsen performance. In our work, in order to adapt the neural network inverse learning approach to nonlinear phase systems, we propose an alternative input selection that forces the neural network to learn a stable approximate inverse of the baseline system. We show in our work that the map approximated by the neural network module in the nonlinear phase case is related to a model-based approximate inversion approach for linear systems. But in our case, we do not require a model of robot baseline system and can be applied to moderately nonlinear systems. In the first part of the thesis, we explored how we can train a neural network offline to enhance the tracking performance of a single robot. In the second part, we explore how we can leverage the experience from one robot to enhance the tracking performance of another robot to avoid relearning from scratch. We consider the following setup, where the closed-loop source and target baseline systems are represented in the following form. We assume that the source and the target systems are minimum phase and have well-defined and the same relative degree. We first precascade an inverse module trained on a source robot to the target baseline system. Our question is that if we have the module trained on the source system, can we leverage this experience to achieve high accuracy tracking for the target robot system without relearning from scratch? In our work, we propose an online adaptation approach. In particular, we place an online learning module in parallel to the offline neural network module. The online learning module takes in the current state of the robot, the desired output, and the reference from the offline module, and it computes a reference correction for the target baseline system. Using the same inverse learning formulation, we can show that the map represented by the online learning module takes the following form. Here, alpha is the adaptation gain, and EP is the predicted tracking error are steps ahead. The error prediction is provided by an error predictor trained using online data. Intuitively, this online learning module looks ahead into the future and provides an input adjustment based on the predicted tracking error to further enhance the tracking performance of the target baseline system. To better understand when it is safe to transfer experience, we propose an approach to characterize the dynamic similarity between two robot systems. We show in our work that, in the linear case, the overall learning-based system is bounded input on the output stable if the following condition is satisfied. Here, S2 is the characterization of the system similarity that has values closer to 0 when the two systems are more similar, and beta can be thought as a characterization of an upper bound on the error in the online learning module. When the online learning module is active, this condition implies that if the source and the target systems are more similar, then there will be a greater margin for selecting the adaptation gain and higher error tolerance for the online learning component. We tested our approach with quadrotor impromptu tracking experiments. We verified the approach on 10 arbitrary hand-drawing test trajectories. The gray bars correspond to the tracking error of the target baseline system. If we directly transfer the neural network module from the source robot, we can reduce the tracking error of the target system by an average of 46%. If we further augment the online learning module, the tracking error of the target baseline system is reduced by an average of 74%. To validate our approach, we performed two additional sets of experiments where the source and the target robots are respectively enhanced by their own neural network modules trained from scratch. The performance achieved with the proposed offline-online learning approach is comparable to the scenarios, but only uses minimal data collected online. To summarize, in this work, we presented an online learning framework that enables the inverse dynamics module trained for our source robot to enhance the tracking performance of a target robot. With the goal to better understand when transferring experience is safe, we propose an approach to characterize the similarity between two systems and study the role of system similarity in the cross-robot transfer problem. The efficiency of the transfer learning approach was demonstrated in quadrotor impromptu tracking experiments. In the last part of my thesis, we proposed a neural network adaptation technique to bridge the model reality gap and thereby enable model-based control techniques to be applied in presence of dynamic uncertainties. We first show the architecture of our proposed approach. We consider a black box robot system with input U and output Y. We augment this unknown system with the Lipschitz network adaptation module with the goal to make this overall system from input U to output Y behave like a reference model. This reference model can be in turn used by a model-based controller or planner to realize a desired objective. This work generally falls under the model reference adaptive control literature. In contrast to typical adaptive control approaches, the proposed approach does not assume a particular parametric structure of the baseline system, and in contrast to other neural network adaptive control approaches, they guarantee stability via the network architecture design rather than relying on specific network parameter initializations. In this work, we consider the robot system and the reference model represented as control-affine nonlinear systems. If we know the dynamics of the robot, then we can derive an input correction map to make the overall robot system behave like the reference model. When the dynamics of the robot is not known, we can design a neural network to approximate the input correction map. The neural network parameters are updated online to minimize the difference between the unknown robot system and the reference model. In our work, we use a special type of neural network called the Lipschitz network, which is guaranteed to have a predefined Lipschitz constant via the network architecture design. From a control theory based on the system properties, we can derive a certification condition on the Lipschitz network module to guarantee stability. In particular, if we assume the robot baseline system is finite gain L2 stable, the uncertain robot system with the Lipschitz network adaptation module is stable if the following condition is satisfied. Here, L is the Lipschitz constant of the neural network, and gamma is the L2 gain of the system. This Lipschitz condition can be conveniently encoded in the design of the Lipschitz network. We demonstrate our proposed approach using flying inverted pendulum experiments, where a quadrotor is expected to balance the pendulum in the upright position. The quadrotor we use in our experiment is an off-the-shelf platform, where an accurate model of the onboard control system is not available. We first show the baseline system performance, which is an LQR controller designed based on a simple acceleration dynamics model. Due to the model reality gap, the standard model-based controller cannot stabilize the system. Now, if we augment the quadrotor system with a proposed Lipschitz network, we can make the system behave like a reference model and thereby bridge the model reality gap for the LQR controller to be successfully applied. So our controller can tolerate moderate disturbances such as wind and tap. The same controller also allows the quadrotor to track circular trajectories while balancing the pendulum in the upright position. To summarize in this work, we propose a Lipschitz network adaptation approach to make an unknown robot system behave like a reference model, which can be used by a higher-level model-based controller or planner to realize a desired objective. The proposed approach does not rely on a particular parametric structure for adaptation, and stability of the proposed approach is guaranteed via the Lipschitz network design. We verified the proposed approach in flying inverted pendulum experiments. Here is a summary of the contributions included in my thesis, which include 3 first-author journal publications at IJRR and Robotics and Automation Letters, as well as 3 first-author conference publications. During my Ph.D., I also worked on a few other projects. One is further investigating how dynamic similarity can affect transfer learning performance. With other colleagues in my lab, we recently completed a survey paper on safe learning in robotics and also proposed other safe learning control techniques such as online learning control barrier certificates. Moreover, we recently released benchmark tools to further facilitate safe learning algorithm designs and comparisons. To conclude, the goal of my thesis was to develop theory-driven approaches that safely and efficiently exploit the modeling capability of neural networks for robot control applications. In the first set of work, we proposed an offline neural network inverse dynamics learning approach to enhance the tracking performance of robot baseline systems. For this work, we looked into how to generate active training trajectories for system data collection, and also extended the approach to non-manifest systems. We then explored how to leverage experience trained on a source robot to enhance the tracking performance of a target robot, and further studied the role of system similarity in this transfer problem. Finally, we proposed a Lipschitz network adaptation approach to bridge the model reality gap and enable standard model-based control techniques to be applied in presence of uncertainties. Overall, in my thesis, we explored learning control approaches that combine control theory and machine learning techniques. We demonstrated in experiments how we can use data to improve performance of classical control systems, and also how to leverage control theory to guide safe and efficient implementations and provide stability guarantees to the learning-based control techniques. There are a few interesting extensions to the thesis, which include incorporation of perception and semantics in the controller design, further investigating characterizations of similarity for nonlinear robot systems that can be efficiently estimated using minimal data online, and extend the proposed approaches to a broader class of robot control systems, such as systems with hybrid dynamics. To conclude, I would like to thank my colleagues from the Dynamic Systems Lab who have been supporting me in my Ph.D. research. I would also like to thank my supervisor, Professor Angela Schoellig, for guiding me through this process. It was a very exciting and memorable journey.